In this problem, we are going to be applying Ampere's law. So this is the problem at the bottom of page 4 of your chapter 28 lecture notes. So I've written down here Ampere's law, and we are going to apply Ampere's law to a solenoid. And this actually is a little bit different than the current carrying loop that we discussed in the previous section. Current carrying loops tend to have a larger diameter compared to their length, and that's going to affect how the magnetic field is distributed compared to a solenoid, which tend to have a smaller diameter and be longer in length compared to their diameter. So we're going to see when we apply Ampere's law to this solenoid that it's going to have a slightly different equation because of that. Now, looks like I've skipped from having an integral to not having an integral, so let me show you the intervening step here. So what we're doing here is we're integrating from 0 to L. And notice that there's a circle here, meaning that there's a closed path. So we are integrating over this essentially symmetric rectangle that I have drawn here. So I've drawn a cross-section of the solenoid here, so you have the wires coming in and out of the page. And so you have to imagine it comes out here, goes in here, comes out here, goes in here. So that there's actually loops that are looping in and out of the page here that make up the metal of the solenoid. And I've drawn this symmetric rectangle around the loop that makes up the solenoid. So my path is going to go through the center of the solenoid, along the side, outside, back, and then come back down the side. So I'm integrating over that path. And I'm doing this in sort of a hand-wavy way. Technically speaking, B does vary with L, but I'll explain how we're getting around that in the next step. So I'm going to put B dl here equals, and I'm using the version with n in it since we have a solenoid with multiple loops to it. And so whenever I integrate this, I end up with this formula here. Now let's focus back on our diagram here. Now remember, the magnetic field lines come through the center of the solenoid and out the back and come around, and they would do so equally on both sides. And what this creates is a magnetic field distribution where it's very strong at the center here, where the one path, part of our path of L is, and much weaker on the outsides. So when we go around our path, we're going to count this part of L, which would be the length of the solenoid, because the magnetic field is very strong there. And we're going to ignore all the other components. So this, and this part of L, because we're going to assume that the magnetic field strength there is very small because the magnetic field lines spread out as you move away from the solenoid. So I'm only counting that portion of L through the center of the solenoid, which would be the length of the solenoid given here in the problem. So this is an approximation, but it works well enough using Ampere's law to give us credible calculations. I've then plugged in my magnetic field strength, the number of turns in the solenoid, and then our magnetic constant, and I'm solving for current, which you can see down here. In your textbook, you might see that there is a variable little n that equals the number of turns in the solenoid per length of the solenoid. I tend not to use this because little n also represents the number of moles, also represents the particle density when we talked about current. So I'm trying not to use that little n, but it is present in your textbook. And that's why you might see the formula written a little bit differently in your textbook.